So let me repeat. Most of the current technology we have is not based on exploiting quantumness. And now you should know, next time when somebody asks you, well, what is quantumness? It's entanglement, okay? So we don't exploit entanglement or superposition in many cases. Laser is really a purely quantum mechanical device, and it utilizes coherence of light. But I think also for laser, if you just are interested in the output and the operation, you can sort of write semi-classical equations. So in some sense, it's not exactly quantum device in the same way as I will explain next. So the idea is that in these new devices, we explicitly use entanglement, so the real quantumness. In fact, superposition is related to entanglement, but let me just talk about entanglement for simplicity, okay? So the building block, the simplest building block of these new devices or this new quantum technology is something called a qubit. And you can actually see what it looks like. I mean, these are now routinely made, even here at Aalto, in Micronova, we make this routinely for the experiments and for the devices that we do. Well, not me, I'm a theorist, but my experimental colleagues. So the qubit is a two-level system, but it's a quantum mechanical two-level system, so it can assume any state. It can be in any superposition of these 0 and 1 states. So it doesn't just have two values, but it can have any value in between. And then when you make a measurement, then it collapses to 0 or 1, okay? So it's like a spin. You can think of it like a spin, mathematically. So the computers we have specifically are not quantum mechanical at all, because in fact, we can all make a computer here, okay? So if I tell you that 1 means hand up, 0 means hand down, we can actually make a computer with each of you acting as a bit in the computer, and we can do a calculation, okay? So for a digital computer, a binary computer, you don't need any electronics. You can do it with anything you want, even with humans. I think the Chinese population would make a powerful computer, but of course that would be somewhat difficult to control. So, but in principle, you can do this with your friends. You can make a small computer and do some calculations. If you don't believe me, it's not difficult. But of course, in practice, our computers are electronic because it's fast and cheap and small. But a quantum computer is something completely different. So it really is something completely different, because the basic building blocks are not bits, but they are qubits. And that means that so every bit in a standard computer can have two values, yes or no, right? So you can store one bit of information. Either there is something or there's nothing there. However, in principle, since a qubit can be in a superposition of any of the two states, you can store a huge amount, almost infinite, theoretically, into a single qubit. And then you connect these qubits, so you entangle the qubits. Remember, for entanglement, you need more than one quantum system. So one qubit can be in superposition of its own states, but then you can entangle multiple qubits. And then you get the real quantum effects, okay? Real quantumness, like I said. And then you do quantum operations, and at the end you collapse these qubits and you read the answer. So the advantage is twofold. With just a relatively small number of qubits, you can you can handle a huge amount of information, and then because all these operations happen simultaneously, you can do like kind of parallel computing at the same time. So you can search for all the possible options at the same time. And that's why this would completely revolutionize computation, and you could decrypt all the highly encrypted passwords and all kinds of things. The last thing I want to talk about, so my research relates to the quantum computers, but also something called quantum thermodynamics. So let me spend the last couple of minutes discussing why. What does quantum thermodynamics mean? I mean, of course, you can put the word quantum in anything you want, but it doesn't mean anything if you talk about quantum consciousness or, I don't know. I mean, it doesn't. So what does it mean if I talk about quantum thermodynamics? Well, actually, it's a well-defined field of research. I think everybody knows thermodynamics. We all look at the temperature, maybe multiple times a day. That's what thermodynamics is about. It's about temperatures and engines and heat and work. And of course, this really gave us the Industrial Revolution, with the mechanical engines. It is fully macroscopic theory. So this was developed well before any microscopic theories, and it's a beautiful mathematical theory, actually. But it has no quantum mechanics, no microscopics in it. But it's been extremely successful. So the question is, if we go into really small systems, these quantum systems, can we try to understand them somehow in a similar way? And at first, it looks like there's a contradiction, because thermodynamics is the theory of macroscopic systems, and quantum systems are microscopic. So can you even try to describe these microscopic systems with something similar to thermodynamics? And that's an interesting topic. The reason that this is important is that we can actually build these devices. So this is a device built here by my colleague Jukka Pekola at Aalto. It is a quantum heat, what they call a quantum heat engine. So there is heat flowing between the red and the blue circles, and the red and the blue circles just indicate temperatures, but there's a qubit in there, in the center of each circle. So these qubits are at different temperatures, and then there's heat flowing, and there's a way to control the heat flow. You can see the valve in between. There's a way to control the heat flow between these two qubits. So this thing works like a mini engine, okay? Quantum mechanical engine. It's a real quantum mechanical engine. The question is, because of laws of quantum mechanics, its behavior is different from the classical engines. And in order to understand how this works, we need to understand how does the heat flow in this quantum world, what is the energy of the system, what is the work, what is the entropy, all these things that we need for thermodynamics, and that's what we've been working on. It's a really interesting topic because it's not so trivial to try to understand these concepts for microscopic systems. But let's say we want to say, how efficient is this machine? Is this machine somehow more efficient than any classical machine? To answer that, we have to know the power output of that machine. So we need to know how much heat is generated, how much work is put into the machine, or how much work does the machine do. You see, we need these thermodynamic quantities. So that's an interesting research topic.